Contrary to popular belief, Grok-4's breakthrough wasn't just one single innovation, but a combination of 6 key factors acting in synergy. These pillars of success include unprecedented hardware infrastructure, exclusive access to real-time data streams, and a revolutionary model architecture. This multifaceted strategy allowed xAI to achieve a performance leap that caught the entire industry by surprise. xAI established its hardware supremacy by creating Colossus, a supercomputer built within a converted 785,000 square foot Electrolux factory in Memphis, Tennessee. This facility houses an astonishing 200,000 NVIDIA GPUs, a number that dwarfs the resources of competitors like Meta's RSC and the Frontier supercomputer. The sheer scale of this operation provides the raw computational power necessary for training models of unprecedented size and complexity. The Memphis experiment proved to be a masterstroke in rapid scaling, allowing xAI to bypass the typical delays and costs associated with building a traditional data center. By retrofitting an existing factory, the company was able to deploy its massive GPU cluster in a mere 19 days, a timeline unheard of in the industry. This unconventional approach gave xAI a crucial speed advantage, enabling them to accelerate their research and development cycles significantly. Beyond raw computational power, Colossus's GPU armada of 200,000 units enables a highly sophisticated and massively parallel processing architecture. This setup allows for the training of models with an extraordinary number of parameters, far exceeding what was previously possible. Furthermore, the custom-designed Spectrum-X Ethernet system minimizes latency and maximizes data throughput, ensuring the entire cluster operates as a single, cohesive unit. The hybrid GPU strategy, which combines NVIDIA H100 and H200 GPUs, is a deliberate choice to optimize the entire machine learning lifecycle. The H100 GPUs are primarily leveraged for their exceptional performance in model training, while the newer H200 GPUs are specialized for high-efficiency inference. This division of labor ensures that both the learning process and the deployment of the final model are executed with maximum performance and cost-effectiveness. Coordinating a 200,000 GPU cluster requires groundbreaking software techniques that go far beyond standard parallelization methods. xAI likely developed a sophisticated dynamic routing system that adaptively allocates tasks across the network, ensuring optimal workload distribution. Additionally, a hierarchical processing model and sparse attention mechanisms are probably used to manage the immense flow of information efficiently. The integration of Tesla batteries represents a new power paradigm in data center energy management, moving beyond simple backup capabilities. These batteries act as a crucial buffer, smoothing out the extreme energy demand spikes that occur during high-intensity AI training. This system not only ensures operational stability but also facilitates the seamless integration of renewable energy sources, creating a more sustainable and resilient power infrastructure. Consuming over 300 megawatts of power, enough for 300,000 homes, has profound implications for continuous model training. This immense energy budget allows xAI to run training cycles without interruption at the highest possible intensity, a critical factor for developing state-of-the-art models. Such a scale, however, also raises significant concerns about grid stability and the environmental impact of CO2 emissions. The architectural secrets of Grok-4 lie in a fundamental departure from conventional model design, focusing on what xAI calls first principles reasoning. This approach is not an incremental improvement but a complete rethinking of how an AI processes information, leading to enhanced logical consistency and deeper analytical capabilities. The architecture likely incorporates a mixture of experts and hierarchical processing to achieve this new level of understanding. First principles reasoning is technically implemented through a combination of multi-agent systems and advanced neural network structures. The Grok-4 Heavy version, for example, utilizes multiple AI instances that collaborate to analyze problems from different perspectives. This is complemented by novel attention mechanisms that allow the model to focus on the most critical pieces of information, ensuring logical coherence. The model's ability for hierarchical problem solving stems from its capacity to break down complex questions into their most basic, indivisible components. It constructs a logical tree, starting from the foundational principles and building up to the final solution, ensuring that every step is validated against the core truths of the problem. This method avoids the shallow pattern matching that plagues many other large language models. In the Grok-4 Heavy version, multi-agent collaboration is governed by a sophisticated dynamic routing mechanism that assigns specific subproblems to specialized AI agents. These agents work in parallel, each tackling a piece of the puzzle, and their findings are then synthesized by a master agent. A continuous feedback loop allows the agents to refine their collective understanding and resolve conflicts, leading to a more robust and accurate final output. The massive 130K context window is enabled by significant architectural changes, particularly the implementation of sparse attention mechanisms and a more efficient memory architecture. Unlike traditional attention models that process every token in the context, sparse attention focuses only on the most relevant segments, drastically reducing the computational load. This allows the model to maintain a much larger short-term memory without a proportional increase in processing requirements. An expanded context window revolutionizes advanced document analysis by allowing the model to process entire books, research papers, or even complete software projects in a single pass. This holistic view enables a much deeper understanding of the material, as the model can identify long-range dependencies, track the evolution of arguments, and grasp the overall structure of the information. It moves beyond simple keyword extraction to genuine comprehension of complex documents. Native tool integration through reinforcement learning is fundamentally different from API-based approaches because the model learns how and when to use tools as part of its core reasoning process. Instead of simply calling an external service, the model develops an intuitive understanding of a tool's capabilities and limitations. This is achieved through a sophisticated reward shaping mechanism that encourages effective and efficient tool use. Integrating web browsing directly into the model's reasoning process offers significant technical benefits, most notably a reduction in latency and an improvement in contextual processing. Because the model doesn't need to make external API calls, it can access and process real-time information almost instantaneously. This seamless integration allows the model to incorporate the most current data into its responses, making it far more accurate and relevant. Grok-4's training revolution was fueled by a combination of continuous learning on live data, an exponential increase in computational power, and innovative reinforcement learning techniques. The model was not trained on a static dataset but was constantly updated with real-time information from X, formerly Twitter. This, coupled with a massive 200,000 GPU cluster, allowed for incredibly rapid iteration and improvement. The X data advantage provides XAI with a uniquely rich and diverse training dataset that is updated in real time, a crucial factor that is often underestimated. This constant stream of information, encompassing everything from academic discussions to colloquial slang, gives Grok-4 an unparalleled understanding of current events and cultural nuances. The sheer volume and variety of this data are key to the model's sophisticated contextual understanding. The model learns to understand nuance like irony and sarcasm by analyzing the vast and diverse conversations on X. By processing millions of daily interactions, it identifies patterns in language use, context, and emotional expression that signal non-literal meanings. This ability is not explicitly programmed but emerges from the model's exposure to the complex and often subtle ways humans communicate. A continuous training strategy with a real-time learning architecture fundamentally differs from static training by allowing the model to evolve constantly. Instead of being a fixed snapshot of knowledge, the model is a dynamic entity that adapts as new information becomes available. This approach ensures the model remains current and relevant, but it also presents significant technical challenges in maintaining stability and avoiding catastrophic forgetting. The primary technical challenge of live data integration is ensuring model stability while continuously incorporating new information. XAI likely employs an adaptive architecture that can assimilate new data without overwriting or corrupting its existing knowledge base. This might involve techniques like knowledge distillation and elastic weight consolidation to gracefully merge new insights with the foundational model. The innovative reinforcement learning in Grok-4 utilized a meticulously designed reward-shaping mechanism to encourage high-quality, tool-assisted answers. The system likely rewarded the model not just for correct final outputs, but also for the efficiency and appropriateness of its tool usage throughout the problem-solving process. This focus on the entire reasoning chain, rather than just the result, fosters a deeper and more robust understanding. The model's ability to learn from its mistakes is implemented through a sophisticated self-correction process that analyzes the discrepancy between its output and the desired outcome. When an error is detected, the system traces the reasoning path that led to the mistake and adjusts the underlying weights and biases to prevent similar errors in the future. This iterative process of trial, error, and refinement is central to the model's continuous improvement. Strategic scaling is XAI's core philosophy because the company believes that emergent abilities and qualitative leaps in performance only appear at massive computational scales. This is not just about doing the same things faster, it's about enabling entirely new capabilities that are impossible with smaller models. The aggressive expansion is a calculated bet that size is the single most important factor in achieving true artificial general intelligence. The million GPU vision is driven by the hypothesis that at such a scale, AI models will begin to exhibit emergent capabilities that we cannot yet predict, potentially including forms of common-sense reasoning and true creativity. This massive increase in parameters and computational power could unlock qualitative shifts in intelligence, moving beyond pattern recognition to genuine understanding. The goal is to cross a critical threshold where the model's capabilities are not just incrementally better, but fundamentally different. The real estate strategy of choosing Memphis was a calculated move to create an AI capital by leveraging a unique combination of local advantages. The city offers access to cheap and abundant energy from the Tennessee Valley Authority, a business-friendly regulatory environment, and a central location with excellent logistics. These factors create a significant competitive advantage, allowing XAI to scale its operations more quickly and cost-effectively than its rivals. Favorable energy and regulation in Memphis provide a powerful competitive edge, as the low cost of electricity directly translates into lower operational expenses for the massive Colossus supercomputer. The Tennessee Valley Authority's reliable power grid is essential for maintaining the continuous, high-intensity training required for cutting-edge AI research. Furthermore, a streamlined regulatory environment allows for rapid construction and expansion, minimizing bureaucratic delays. The speed-to-market imperative is critical in the current AI landscape because the pace of innovation is so rapid that perfectionism can lead to obsolescence. By prioritizing rapid iteration and deployment, XAI can gather real-world feedback more quickly, learn from its mistakes faster, and stay ahead of the competition. This agile approach recognizes that in a fast-moving field, being first is often more important than being flawless. Controversial by design, Grok-4 leveraged its unique philosophical stance as a key differentiator in a market of increasingly sanitized and politically correct AI models. By reflecting the views of Elon Musk on certain topics, the model projects a consistent and recognizable personality, which can be more appealing to users than a bland, neutral tone. This calculated risk is a core part of its strategy to build a loyal user base. The model's truth philosophy represents a significant departure from industry norms by prioritizing uncensored responses over political correctness. This approach aims to provide a wider range of perspectives on controversial topics, mirroring the complexity of real-world human discussions. While this strategy carries the risk of generating offensive content, it is also a key part of the model's value proposition to be a source of unfiltered information. To manage the risks of uncensored response generation, Grok-4 likely employs a sophisticated set of guardrails that operate on a different philosophical basis than its competitors. Instead of broad topic restrictions, the system might focus on identifying and flagging direct threats or harassment while allowing for a wider range of opinions and even offensive humor. The primary safeguard is the system's ability to learn and rapidly correct its behavior based on user feedback and internal reviews. The system's rapid response capability is a testament to its highly agile and adaptive architecture. When the chatbot produced anti-Semitic remarks, XAI was able to deploy a corrected version within a day, demonstrating an impressive ability for immediate course correction. This is likely enabled by a continuous integration and continuous deployment pipeline that allows for near-instantaneous updates to the production model, combined with a robust system for monitoring and flagging problematic outputs.